Morning, everyone. I hope you're doing well. Um, got some new directions we'll go in today. But before we do that, I'm going to do a little bit of wrap up of what we've covered so far and some of the gaps that we will come back to later on in the course. So let's look at what we've done. So we have looked at the heat equation. In one spatial dimension, and now after Thursday's lecture in more spatial dimensions. With initial conditions. And I'll say homogeneous boundary conditions of various types. Dirichlet, that's where the values of U are specified. Neumann conditions, that's where the derivatives are specified on the boundary. In higher dimensions, it's the normal derivatives. And then the mixed Robin conditions. But we've only looked at ones where there's sort of zero forcing. We've also looked we've also looked at the Poisson problem. Well, you can think of the first boundary value problem that we looked at in 1D as a 1D Poisson problem. Typically, it's only called a Poisson problem if it's in higher dimensions. You can see right away that this can arise as a steady state of the heat equation. That we also looked at with homogeneous boundary conditions. The techniques, we saw Green's functions and Duhamel's principle in there. The Duhamel's principle is what allows us to solve the pure initial value problem. And from that, read off the solution to the interior forcing problem. But mainly what we've looked at are series solutions. And so that's been the main technique that we've used. There's a missing piece, which we will come back to. So I'll say to finish off this discussion. So the discussion of those problems, we would have to look at non-homogeneous conditions. So if I looked at the 2D Poisson problem, except with zero data, but instead looked at the complementary problem where I specified data on the boundary. This is called the Laplace problem. That's a problem that we're still missing. We could look at the next problem I'll show you in higher dimensions, but even in 1D, we haven't looked at it yet. If I look at the 1D heat equation, so When I say 1D, I mean one spatial dimension. There could be interior forcing, but we know how to handle that. There could be initial data, but we know how to handle that. What we haven't handled yet is non-homogeneous boundary data. So what if we gave data on the boundaries? How would that look? So these are two problems that we will come back to later. Later in the course. The kind of techniques that we're going to use are transform methods. We'll look at Laplace and Fourier transform methods to make some progress on those. What we're going to start with today, just so that we've got something different, we're going to start looking at hyperbolic problems. And in the lingo, the heat equation, this is a parabolic problem. Laplace problem and our 1D boundary value problem you could call elliptic problems. And so hyperbolic problems, these are ones that are going to be have wave type behavior. And you notice we haven't seen wave type behavior in any of the models that we've studied so far. Before we go on to that, since everyone is so quiet, I have a poll for you. So let's do a poll just to see if people are awake. And this is a question about the system that the teaching assistant and I have in place to have questions asked and answered during the lectures. This is just a poll to see how well that is working.
Questions are not what?
Oh, I don't know why that got cut off. Does not work for me. My questions are not being answered, is what it's supposed to say. That's the it's not working for me answer. Okay, we've had about a minute. There are a few people who haven't registered yet, but I'll end here. It looks like it's working okay for most people. This is an anonymous poll, so I can't see who has said what. But if the person for whom it's not working, if you've got any ideas of what we could do to improve it, send me email or post something on Piazza or whatever. Start a discussion on how we can improve this. Okay. Hyperbolic problems. This is, we will get to the wave equation at some point, but we're going to start off with some more model problems, things that will lead us up to the wave equation. And so I'm going to have something that I'm going to call a wave equation, but it's a one-way wave equation. And I'm not going to motivate this from a sort of physical context. I'm going to write down the behavior that I want, and then I'll identify the partial differential equation that has that, whose solutions have that character. So I'm going to have time dependence. I'm going to want to have the following behavior. I'm going to want to be able to give an initial profile to the solution. And I want the solutions of the partial differential equation to have the property that that profile will move with constant speed, 1. I'll normalize things so that it has speed 1 to the right. So I want this thing to move without changing shape. With speed 1 to the right without changing shape. So with that in mind, I can actually write down the form of the solution I want to come out. If that was the initial conditions, then I want the solution at later time to be the translation to the right at speed 1 of that profile. So there you go. I've written down the solution. This is a little bit different than what we've done before, where we've had a physical phenomenon where we figure out what the PDE comes from. Now we've got this more abstract phenomenon that we want. So now I'm going to ask what PDE gives this solution. And I can go, well, let's take some partial derivatives and see if we see a pattern. Okay, it won't be very long. I'll just have to take the derivative of the initial conditions with its argument. And then by the chain rule, I'll get a negative sign. And I can take the derivative with x, and I get a similar looking thing with a plus sign. So the PDE I want is just ut plus ux is equal to 0. Okay, and I can call this the one-way wave equation. Shortcut W1. Okay, one of the themes that we had at the beginning of the course was this idea of weak solutions. And as soon as we know that the solution of this thing, I can just write this way, right? Wow, there's a delay for me with stuff coming up. I don't know if it's a delay for you guys coming up. But since we've got this form, right, I know that there's a natural way to define weak solutions. Remember, weak solutions are ones which you sort of feel should satisfy the problem that you've written down, but don't have enough derivatives to actually take and put into the equation and have it all, actually be equal to 0. And so if we go back here, and I think of initial conditions I have that are discontinuous, Well, I can move that profile to the right with speed 1. And get a solution that makes sense, but it won't satisfy this differential equation at every point because there's no derivative at that discontinuity. Okay. I'm going to take a bit of a detour into boundary conditions, and then we won't discuss them for the rest of the class, except maybe in an assignment question. I'll say for problems like this, boundary conditions, I'll say are interesting. Let's look at a problem where we're confining our attention to x equals 0 to 1. And let's just think about it, right? Everything is moving to the right with speed 1. And so I don't need any boundary conditions over here. Right? It's the wave, whatever is happening in the inside is moving to the right. That is what's going to happen. And now let's just think. Let's look at where the information from the initial conditions can go, right? The initial conditions are moving with speed 1. And so if I look at this line, which will be x is equal to t, if I look in here in this region, in that region, the solution is determined by the initial conditions. With x given between 0 and 1, right? Initial conditions between 0 and 1. Once you get up to time 1, that means you're looking at the initial conditions at, well, the only one that still is in the region where you've defined them is at x equal 1, right? That's this point. That's the information that came from here, from x is equal to 0. And so clearly, you're going to need some sort of boundary information here. I'm just going to give Dirichlet data. And then if you look at this region over here, everything up here, that blue region, the solution is going to be determined by the boundary conditions. Okay. So that was a little bit of a teaser about boundary conditions. Let's forget about boundary conditions for a while. Oh, hang on. For now. Okay, and what do I mean by forget about boundary conditions? Well, I'm just going to look at the problem for all x. I'm going to consider this problem defined for all x. So this is how I'm going to say there's no boundary conditions, right? And this problem has a name, right? It's an initial value problem with no boundary conditions because you're considering it in infinite spatial dimension. This thing here is called a Cauchy problem. Okay, so we're going to look at some Cauchy problems for first order PDEs. In the notes, there's some generalizations of the definition of Cauchy problems for other places where data is given and for higher order equations, and you can read that. Okay. Let's go back and look at our one-way wave equation. And we know we had solutions that were u of x and t is a u0 of x minus t. Let's look at this a little bit differently, okay? I'm going to look at these lines, which are lines in the xt plane. I'm going to look at those lines in the xt plane. These are lines with slope 1. And they have an x-intercept, which I'm going to call s, right? Well, s is not x, right? But I can look at these lines. This is not going to be x, is t plus s. And now I'm going to change coordinates. So instead of having coordinates x and t, I'm going to have coordinates s and t. And if I look at it that way, right, I'm going to get, so s is constant on this line, even though x and t are both changing. I can look and go u at s and t, if I change those coordinates, it's just going to be the initial conditions that are at that point. Okay, so we're going to generalize that a little bit to slightly more complicated problems. And let's look at one of them. So I'm going to have a new problem. It's going to have wave-like behavior. And the difference is, instead of just a 1 here, I'm going to have a coefficient that can vary. Right, and I guess I should tell you this function, this is going to be a given, right? So you're going to know this function everywhere. And I haven't shown you yet, but you will see that this is going to be a varying speed of propagation. Okay, so I had these curves here. X is a function of t, right? I could say maybe more correctly, I've got these curves. X is a function of t and s, right? But I'm really thinking of these curves as x is a function of t for given s. It's a bit of a subtlety, but let's think of them that way. Hang on a sec, I'm gonna shut my window. There's some noise outside. Okay, hopefully they're doing some sort of construction thing outside my office window. So we're gonna look at this, the same idea. So we're gonna look for curves, x of t. For the simple problem we started with, the curves were just straight lines, okay? Right, with slope 1. Now we're going to look for these kind of curves with a starting location, which is S. So if we did this game for this problem, the curves we would look for would be x is t plus s. They'll be a little bit different in this case. Well, let's have a look and see what happens. Let's consider u of x of t and t. I'm allowed to do this, right? I'm going to say this thing has a solution. I'm going to look at that solution restricted to a curve in the xt plane, right? Okay, so let's have a look and see what happens. If I look at du by dt, right? This is now not the partial derivative of u with respect to t, which is right? This thing is how u is changing just as I move in the t direction. This thing is how t is changing as I move along the curve x of t and t. I haven't told you what this curve is yet. I'm going to figure out how that curve should behave to simplify the partial differential equation to an ordinary differential equation. Just like along these curves, we realized that du by dt was 0. It was exactly the same as the initial conditions that you have. Okay, so let's look at du by dt. Now I have to take some derivatives here. That is dx by dt times du dx plus du by dt, right? And if I compare to this, I see that there is an interesting curve to look at. That's the one that's moving with speed c of x of t. So let's consider curves where dx by dt is equal to c of x and t, right? So if I look at curves that look like that, right? So here I am, I'm following a curve, but I'm following a particular curve that has this property everywhere. This is a solvable ODE as long as I give initial conditions, and of course, motivated by what before, I'm going to give initial conditions somewhere on the initial line, right? Okay, then du by dt then becomes, let's go back here, dx by dt, that's c of x and t times du dx plus du dt, right? And by the PDE, this is 0. Okay, So this just says if you have lines that have this behavior, and these lines that have this behavior, these are called characteristic lines. If you look at lines that have that behavior, the solution doesn't change. And that means that if I look at u of x and t, these are following the characteristics. This is just going to be u0 at wherever I started from, right? I have initial data here. I follow this curve. Right, and I know that the solution is constant on those curves. And I know a value here, right, at time 0. I've been given initial conditions in this Cauchy problem. And so I know the solution has to be constant. It has to be this value all along that curve. Now, of course, this is not true for any curve you follow, right? It's only for the curves that have this property, the curves that follow this local speed of propagation. Okay, so it's a very different technique, okay? But it has at least one similarity with the series solutions that we've looked at before, and that is that we reduce a partial differential equation to a family of ordinary differential equations, right? I only have to solve ordinary differential equations. I just have to solve an ordinary differential equation for the characteristic paths. And then I have to solve an ordinary differential equation for the behavior of the solution on those characteristic paths. Here, the ordinary differential equation is very easy. It's du dt is 0, okay? But in general, we can have a little bit more complicated behavior. Anyway, this is the form of the solution that comes out, right? And if I wrote it in a little bit more detail, remember all of these characteristics start somewhere. And this is the form that comes out. And I've got some examples to show you coming up, of course. This is the form that comes from that technique, and it is an implicit form. And sometimes, right, what you want is to take this form and convert it to, u of x and t, right? And this is sometimes possible to do analytically. And sometimes not. But either way, you'll get insight into how the problem behaves. Okay, I think there's a good question coming up. So the question is, does every point x of t follow on one of these characteristics? And the answer is yes, at least for short time. Okay. There are examples where you can have, okay, because even though this PDE is linear that we started with, it's got superposition. You can check that. Even though it's linear, these characteristic equations are not linear. Okay, and so you will potentially have some cases where you only get existence for short time. Okay. Okay. Good question. Excellent question. The kind of theoretical results that get shown for these kind of equations are that there is a unique solution in the neighborhood of where the initial conditions are given, right? And initial conditions could be a little bit different than just a straight line x and t. Okay. Okay. Let's do some examples. I'm going to have ut plus cosine t times ux is equal to 0. And I'll do the Cauchy problem, which means I have initial conditions given. And this is for all x. Okay, so let's solve for the characteristics. Okay, so there's no x dependence here, so this is just an integrate. There's no real ordinary differential equation to solve. We're just integrating. I'm going to get, with the initial conditions, I'll get x is sine t plus s. Okay, so by construction, u will be constant on these curves. And so I'm going to have u at sine t plus s, and t is equal to u0 of s. Okay. Here, it's easy, right? If I want to write s as a function of x and t, that's pretty easy, right? I got s is x minus sine t, right? And so now I've got u of x and t. I'd have to figure out what s corresponded to that. So it's just u0 of x minus sine t. Okay, so let's have a look. Let's see if I can draw this picture. I don't have this picture in my notes, I don't think. Right. Okay, so now I have to see if I can actually do this. I'm used to drawing the sine t graph with the axes the different way. So if I start here and I'm doing x is sine t plus s, and s is 0, I'm going to have, once I get to time pi, I'm going to come back. So I've got characteristics that look like this. And there's no complicated x dependence, right? Or s dependence, I guess I should say. All the characteristics have the same shape. They're just shifted. right? And on these curves, u is constant on these curves. These are curves we're calling characteristics. Now you can see if I want the solution here, I have to work backwards to figure out what its value was at time 0. And that's where this expression comes from. We did it by algebra, but you could have worked this out from this picture. Okay, so now you kind of have the idea from this picture how solutions of this problem behave. They're just the initial conditions, and they just slosh back and forth, right? There's no net motion in this example. Okay, let's do an example where you can, but let's say we won't work out this inverse problem. We're just going to look at the parametric form that comes out. So I'm going to have a different problem. This time, oh, there's another question coming, I think. Oh, will this method still work if we have a weak solution for x of t? Okay, so now this is interesting, okay? So I'm going to say the student is asking a different question than can we have weak solutions? So I'm going to come to the student's question, but let me talk about it. When we talk about a weak solution here, we're talking about a solution where this thing is discontinuous. Initial conditions are discontinuous. And of course, there's no problem with that, right? If I had a discontinuity here, right, I just have a discontinuous solution, across this line. There's no problem with that, right? The question is not really, I wouldn't call it that this is about a weak solution, but the question is, what if you generalized the speed to be discontinuous, okay? Well, let's just think, right? I could have a speed 1 over here and speed 0 here. And then you could see my characteristics would look like this, but straight up over here. And there would be a gap in the middle where there was no solution, right? No solution in here because there's no information coming from the initial conditions in that point. C being discontinuous is, this is discontinuous in X. If it's discontinuous in T, as the student asked, I think you're okay. Now I'd have to think about it. Anyway, good question. Did I answer your question? Okay, good. So let's look at another example. Now I'm going to have the speed depending on X, but not T. That's going to lead us to a kind of ODE that we can solve. So now I'm just going to pattern match with this technique. I'm going to look at the characteristics. They're going to satisfy. Well, I'm always going to start them off somewhere on the initial x-axis. And they're going to satisfy dx by dt is this speed. Oh, I got the initial conditions already. And this is what's called a separable equation. Now you got to think back to Math 215 or whatever your first ordinary differential equation course was. It's a separable equation. In fact, it's an autonomous equation. That is that the right-hand side, okay, I just have, I'm going to short circuit the question. Just my X wasn't drawn very well, but yes, that should be a UX. Okay, thank you, thank you. Autonomous equations, these are ODEs, where the right-hand side does not depend on T. Or the independent variable, whatever it's called. And autonomous equations are automatically separable, and so you can use this technique. And do you remember how this technique goes? Separable equation. There's a mnemonic. And if you don't know what mnemonic is, it's a way to remember the technique. The way to remember the technique is that you can cross multiply by dt and the other stuff and get dx times 1 plus x squared is equal to dt. Separable means you can do this and have only x stuff on one side, only t stuff on the other. And of course, this doesn't make any sense, but it's the way to remember the technique, right? It's a way to remember the technique, which actually has a more rigorous description, but leads to this process. And if you've only got x's on one side and t's on the other side, then you can integrate both sides. And you get x plus x cubed over 3 is equal to t plus a constant. And this constant, you work out at t equals 0, where x should be s. And so this constant is s plus s cubed over 3. So this determines s of x and t uniquely. Well, except that you would have to solve a cubic equation and pick the right root. And there is a formula for the roots of a cubic. You can use the formula to pick the right root, but I know there's always some student out in a class, almost always, who knows the formula for a cubic, but I don't know it, right? So at this stage, I'm just going to say in practice with that root, then you can work out that u of x and t is equal to u0 of s of x and t with that root. Okay, but now I don't want to go into ugly formulas with cube roots. I want to go even without this formula, you can see interesting things about the behavior. Let's look at this term, which was here, right? This is this speed term, right? And let's just look at that as a function of x. So this is not t. I'm just graphing this one. I think there's a question coming up. I saw something. How do I know which one is the right one? The right one is, okay. Solve a cubic equation with the right root. Well, okay. So how do you know which one is the right root? Well, at t equals 0, I should have s is equal to x. Right, and then the right root is the one that continues smoothly in time from this one. And okay, so now do I know how to prove this right off the top of my head? Because I don't have it written out, but roots of this, so looking for s as a function of x and t, the roots don't cross, right? So once you've started at the right one, then if you continue smoothly, you'll pick the right one. Now, maybe that will be clear from the cube root formula. I'm not sure about that, but at least mathematically, it's clear which root you should take from this continuity argument. Does that answer your question? I'm not going to ask you to use the cube root formula ever. At most, what you should do sort of for practical computations is, you would use root finding, and once you have the root at time 0, you can use it to root find for small times, and then you can continue on that way, always picking out the right root with your Newton's method. Okay, so now I'm going to look at this speed, 1 over 1 plus x squared, right? Right, and I'm going to notice that the speed goes to 0, and it has a maximum of 1 at x equals 0. Okay, the other thing I'm going to notice is that the characteristics have no time dependence. Okay, in terms of their shape. So I can now go to the xt plane. Now I'm going to draw characteristics, right? And I'm going to go, wow, the shape only depends on x, right? They're moving fastest with speed 1 at x equals 0, and then the speed slows down, and vertical lines, these are characteristics that have 0 speed, right? So I know that the shape is going to look something like this, right? And then over here, I'm going to have something that's moving more slowly, and then it'll have maximum speed, and then it'll have exactly the same shape after that, right? So I'm going to have these kind of curves. And over here, I'm going to have something that's moving more slowly, and then hardly moves at all as it increases its x value. So eventually, right, these will all go off to infinity, right? But now I have to think about that. Okay, now I don't know. I just know that as they move to the right, they move slower and slower. And as they cross 0, that's when they pick up and have the highest speed. So we can get a lot of information about this system even without figuring out the exact formula for u of x and t. This is a pretty convincing picture of what's happening. Let's go back to the general case. Right, now I know anything that solves this kind of problem, has these characteristics, and wherever the solution is defined, the value of u is the same as the value from the initial conditions, right, that the characteristic hits. So I know that this problem has a maximum principal. It's a different flavor from the one we had for the heat equation. It's just that all that this equation does is move values around. So you never see values in these solutions that didn't come from one of the initial condition values. So I'll say that if I look at u of x and t, it has to be less than or equal to the supremum of all the initial data, right? And if this could be a maximum if it's actually attained, okay? I'm not sure who in the audience doesn't know the difference between a supremum and a maximum. I can just say, if you have a continuous function on a closed interval, it has a maximum value, an actual maximum value. But if you looked at something like, let me look at this function because it's here. If I'm looking for the minimum value that it has, you would want to say 0, but there's no value of x where that function is 0. So then you have to say, oh hell, what's the minimum version of supremum?
Infimum.
Infimum. Thank you. Yeah. So then you talk about the infimum of that function is 0. That's, the smallest thing that can come out of it, even though it's not attained anywhere. Okay, thank you, whoever shouted that out. These are sort of things now where you can go, even if we don't, actually get a closed form analytic form of the solution, we can get a lot of insight into its behavior looking at these characteristics and some of the properties that we know come from them, like this maximum principle. Okay, so now I'm going to look at a slightly harder problem because it's going to have some right-hand side dependence. So now I'm going to have a ut plus ux is minus u plus x times t. So now I don't have a homogeneous right-hand side, right? I've got some stuff over here. Now, strictly speaking, right, as I write this, if I wanted to sort of be a little bit more consistent, I would put the u thing on the left-hand side, but I'm going to leave it written in this suggestive way, where I'm going to have the same kind of characteristic action happening over here. It's just on the characteristics, I won't have U not changing. I'm going to have U depending on this stuff over here, right? This is still linear in a U. And it's going to be the Cauchy problem again with U0 of X is going to be given. Okay, so I'm going to do the same game I did before. I'm going to look at this along characteristics, right? So here the characteristics are dx by dt is equal to 1. That tells me that x is t plus s. This is back to the one-way wave equation, right? And if I look now at du by dt, right, that's the derivative of the solution along those characteristics lines, right? Then I get the same thing, right? I get du dx dx dt, and that's just 1, plus du dt. And now I can use the PDE to say, hey, along the characteristics, the solution isn't constant, okay, but it's something that I can evaluate. Now it's a little bit tricky here, right? This is really a partial derivative with s being held constant, right? So this is something where I want to write this thing in terms of s, right? So I want to write that as du by dt is a minus u plus t plus s times t, and this is along characteristics. Right, I can draw the same picture that I've drawn before. I'm looking at the solution along these straight lines. I've gone back to straight lines, you know, for this example, just to make one thing easier as I make something else more complicated. Originally, along these lines, we had u being constant, right? But now u's not constant. It's decaying exponentially with some forcing, right? And this is one of those linear equations that we studied before. And so I can just write down the solution. I could do that integral, or I could do the method of undetermined coefficients. Remember, along these lines where I'm looking at these equations, s is constant. So t is varying, but s is just constant. I'm going to get u0 of s plus s minus 2e to the minus t plus t squared plus s minus 2 times t minus 1. Okay, well, so that's the solution that comes out. Hopefully, when I put t is equal to 0, I get that the solution should be u0 of s, and I'm looking at it. It looks like it does. This is just a sort of straightforward solution technique. Again, either way, you write it as a homogeneous plus a particular part, or you use the linear formula that I reminded you of in class a few lectures ago. Okay, and again, in this simple case, we can convert this solution, which is written out in terms of u of s and t, in terms of u of x and t, only because we've got this very simple relationship. Same as before, wherever I see an s, I can put an x minus t. And so I can get a u of x and t is u0 of x minus t, right? So what linear formula were we talking of a few classes ago? That is the, here, let me get a different color. That is, if you've got a ODE that looks like, there's a formula for that. That's Math 215, right? So that's probably what I used, or I might have used the homogeneous plus particular solution idea, which you can use in that case which has constant coefficients. Okay, I'm just converting this now to this formula. So there you go. I mean, there is, if someone said, find me the solution, u is a function of x and t, this would be what you would do, right? But more important, I think, is this idea of the information you're getting from this picture. You know that u is entirely determined on this line alone. And that there's, on that line, there's a natural decay with time constant 1, with some forcing that depends on where you started and what time you're at, right? So you know how information is propagated and how it's changing along those curves. What do we got? We got 6 minutes. Let me give you the general theory. Okay. Here is where you're going to see, why you just can expect sort of local behavior in general. So this is the general theory for first order equations. And why are these first order equations? Because they've only got one derivative, right? One time derivative, one space derivative. Our previous equations had, the parabolic equations had one time derivative, but higher derivatives in space. And the elliptic equation always had second derivatives in space with no time. So here I'm talking about first order equations with a time-like variable. Just because I call it t doesn't mean it actually has to be time, but it has to have behavior like that. So I'm going to have ut, I'm going to have a, so here's my speed. And then I'm going to have some linear behavior in u on the right-hand side, but without derivatives. And then I'm going to have some external forcing. So let's look at what happens in a number of steps. The first one is we're going to look at characteristic curves. We have a time-like variable, so we can look at curves that are x as a function of t, right? So this is going to be dx by dt is a of x of t and t. This is with initial conditions given. So this can be solved for x as a function of, I'll say s and t. We think of it as x as a function of t with s as sort of a parameter, but you know, we can put those two things together. Now I'm going to do the same algebra I did before. I'm going to consider the solution on those characteristic curves. And I'm going to get du by dt. That's ux dx by dt plus the partial derivative with t. That's ut plus, right? This I've already solved so that this is a. Right? And so now by the PDE, that's b of x of t and t times u of t plus f of x of t and t. And I've got initial conditions, right? This is t equals 0 on the characteristic. Right, so this is just the initial conditions at that initial spot. Right, and so this that's an ODE that's solvable for u of s and t. And then the third step, I'll say if possible, solve x of s and t for s of x and t, and then you've got u of x and t is u, this u of s of x and t and t. Okay, so this is the story for initial data and a clear time-like variable t. Next time I'll pick up with a slight generalization of that, where the initial data and the characteristic curves are a little bit more general. And we'll see an example. And this will be our lives for the next few lectures, looking at these first order equations with wave-like behavior. We're going to do some nonlinear ones where you can have shock waves, and that'll probably be about as far as we go. Just in case you're interested, right? I'll just end up with one sort of teaser, right? If you go back to this one-way wave equation that we started with, where, right, I identified the solution, well, I identified the PDE from the solution I wanted, basically, right? But we had this behavior. Right, if you thought of a Green's function for this problem, It's quite different from the Green's functions that we've seen before, where the solution at some later time is some integral over the initial conditions, right? This is quite different, right? This is the behavior at a later time just depends on one point of the initial conditions. So formally, you could say, for people who know what this means, right, that the Green's function for this problem is a delta function with a suitable time shift. But this is just to highlight that the behavior we're seeing in the equations that we're looking at is quite different than the behavior that we've seen before. Remember, there was the difference between just the spatial behavior and then when we put in time. And now we've got a time-dependent problem, but the behavior on the initial conditions is quite different. Okay, so I will leave things here. As usual, I will stay on for the next while answering any questions that you have, but I'll stop recording at this point.